this integration of scientific machine learning leads to more robust, interpretable, and generalized models for which can be better suited for solving problems. Now, we can understand this scientific machine learning is okay. This is actually not working. Just give me a second. I want to reshare my screen. Okay. Okay, now it is fine. So, yeah, what I wanted to show by what is scientific machine learning. Uh, in machine learning, the basic task is to find a model which is able to absolutely predict the experimental data. So, one popular way of doing this is to use a neural network, and where we give the points as the input, and we train the network to compute the output. And what we do in the neural network is we want to optimize the neural network parameters to best so that this our model can best satisfy this experimental data set. So to minimize or to find out the best neural network parameters, this is basically done by this error, minimizing this residual error, which you can see that it is xi theta. Theta is the neural network parameter, and this is the exact or the experimental value. So we minimize this error to find out the best neural network parameter combination that best suits the this given experimental data set. So now we can see from this figure 1, if we are basically giving the data as the input, within the vicinity of the given experimental data set, the neural network is able to fit the given data, and the prediction can be done. But outside the vicinity of this data, the neural network is not able to generalize it, and we can say that it is like overfitting. So now what, so if we have some information about this data set information, we know that from where this data set is generated. So so from this first figure we can see that it is nothing but this is like the data set. The nature of the data set is nothing but is representing the harmonic damped oscillator, which of course can be represented by this ordinary differential equation of second order. So now what? So if we infuse this information, that this data is generated by using this physics. So what will happen? So the researchers basically started working in this direction, that how to infuse this physics into our given data set. Now to do so, what's been done is this. First of all, what we do is we generate a set of input points, which is the input coordinates, fed into the neural network, and then we compute the network output, which is represented with the u, and then the derivative of this output is computed, and that can be done using the automatic differentiation. And further, the residual residual error of this PDE is also computed and infused in the loss function. So you can see from this error here. So basically now the loss function is not only the first part where we are minimizing this unn xi theta minus u2. This is not the exact, this is not the only part. We have added one more term which is nothing but the physics of our equation. So now we see that while when we add the physics of when we add the physics or the PD residual in our original loss function, the approximation or prediction using neural network is more generalized and can be seen that it generalizes even outside the visibility of the experimental data. So this is basically the founding of and this the founding understanding of what do we mean by physics informed machine learning. So yeah, physics informed machine learning is nothing but data, and then we are infusing the physical knowledge of our problem into the system, and then we come up with a new set of algorithm called physics informed machine learning. So now what is physics informed neural network? As I already mentioned, this is the neural networks that are trained to solve tasks represented by any given laws of physics. Basically, physics means we are talking about the nature or representing basically in terms of differential equations. So in basically in traditional neural network, that learns from the data only, but pins are not trained just to fit data, but as well as giving some the physical information also. So this figure is basically presenting the this the architecture of the physics informed neural network, which you can see that this x1 and x2 is the inputs, and it goes uh, uh, to the layers. Let us suppose this is the first hidden layer, and all the computation of the neural network, if you have idea about the neural networks, is being done. And further, u is the output computed by the neural network, and then the automatic differentiation is being done to calculate the derivatives, and the loss function is constructed as the sum of the PD loss plus the boundary condition, and further the training procedure is same. Now to explore this algorithm, we can understand this by considering a given differential equation. So let us suppose we consider a given partial differential equation in the form of equation 1, where n is any differential operator, uxt is the unknown solution, fxt is the source term, and omega is the spatial domain, as well as the 0 to is the temporal domain. So this equation 1 is defined together with the boundary conditions and initial conditions, which is represented with equation 2 and equation 3. Now, the first step in the physics informed neural network is first of all, we approximate the solution. So, what is the solution of this differential equation? Is the uxt. So, what we do is we approximate the solution in terms of neural network, so which we are representing with the u theta xt, where theta represents the parameters, weights, and biases of the neural network. The next, what we do is in the physics informed neural network is, as I have shown in this figure, that the loss function is basically is the PD loss and the loss with the initial and boundary conditions. So the first step is we are constructing the PDE residual. So the derivative, so let us suppose an output is computed using neural network, and then the derivative of this output is calculated, and which we are representing with n of u theta xt minus f of xt. So this basically this term is representing the PD residual. And of course, this residual must be approximately 0 at the collocation point. So collocation points are the points what we generate within the domain, spatial or the temporal domain. So based on the PD residual, further the loss function is constructed. So the total loss is the loss due to the PD residual, which I have already shown by equation 3, and the loss due to the boundary condition and initial condition. So, in particular, we can define all these terms is, so this is the residual PD loss, which is 1 upon NR. So, NR is the set of, so what we do is, we have a domain, we generate a collocation point, first of all, within the domain that we are representing with NR. So, the residual, PD residual is nothing but this is represented with 1 upon NR, this at n minus f at a set of collocation points xi and ti. And similarly, the boundary condition, the loss due to the boundary condition is represented with 1 upon nbc, where this is representing the points on the boundaries that we are generating, and this is the residual error corresponding to the boundary condition. And likewise, for the initial conditions, we generate the set of collocation points, and the residual is again uh, this is the residual error corresponding to the initial condition. So overall, loss is not with respect to the differential equation or the boundary condition. It is representing all PDs, different initial condition and boundary conditions. So once the loss is constructed, now our objective is to train the neural network to minimize this loss. So it becomes an optimization problem where we minimize the loss to by training the neural network. And while training the neural network, what we do is we optimize our neural network parameters to minimize the error and to find out the best solution. So this optimization in pins can be done by any of the optimizers, which is most commonly used is the gradient descent or stochastic gradient Adam, LBFGS. Any optimizer can be used to minimize the loss function and optimize the neural network parameters. Now we can understand this pins for with respect to a particular partial differential equation, which is del u over del t is equals to lambda del u over del x square, together with this initial and boundary conditions. So you can see that it is very much clear from this figure. So what we do is, first of all, we generate a set of collocation points x, and with respect to the this is the spatial points and this is the temporal points. So we fed it into the neural network and compute the neural network output, which is representing as u cap. Now what we do is further we use an automatic differentiation to compute the derivative. So derivative of u with respect to t, derivative of second order derivative, because this is our equation where we require this del u over del t and del 2u over del x square. So we compute the derivative with respect to t, second order derivative with respect to x, with respect to initial conditions, and further del over del n. Now, based on this del over del t and del 2 over del x square, so this is the residual corresponding to the partial differential equation, which is del u over del t minus lambda of this. Now, because if we say u cap is the solution, it will satisfy our equation. So residual must be 0. And this is based on this I, we compute the loss corresponding to this boundary conditions. So overall, the loss, if you can see, this is a sum of tau f and tau b, which is tau b is nothing but initial boundary condition and tau f is our PD. And further, we want to minimize this loss to find out the best training parameters, neural network parameters, which is the weights and biases of the neural network. Right, so this is basically the overall working structure of the physics informed neural network for solving PTEs. Now, must mention that the spins is first of all presented by Risey in 2019, and after that, this method becomes very common and the most popular method nowadays for in deep learning, for particularly for solving the partial differential equations. Now we can see that this is one of the example, which is the Schrodinger equation for together with this initial condition at 0x and the boundary conditions. So the pins has been applied on this problem, and a neural network of 5 layers with 100 nodes per layer has been chosen. And this figure, the figure first figure is representing the predicted solution along with the boundary and the training data. This is a spatiotemporal diagram which is having the 150 data points. And this second figure is representing the exact and the predicted solution reported by Risey et al. In 2019. This is the result I am presenting of their paper, where they first introduced the pins and solved this Schrodinger equation problem. And we can see that this sorry, pins can satisfy the exact solution very well. Now, since we understand what pins is and how we solve the partial differential equation using pins, so what are the advantages basically it offers? It removes the curse of dimensionality. Means the basic problem in numerical methods is like when the dimension of the problem increases, the computational complexity increases, because of course the messes are more, and then uh, the problem is also of higher dimension. But this is not the case with the pins. It can easily tackle with the higher dimension problem, where we are basically evaluating the higher order derivatives even using the automatic differentiation. And this is also advantages because it is not dealing only with the data set, it is also dealing with the physics of the corresponding data set. So it has the better estimation with even the smaller data set, and it is robust to, let us suppose, any noise and disturbance in the data set. And some comparison of the pins with the very like in numerical methods, like with the finite element method, a comparison can be provided where in neural network or in the pins, the basis function is non-linear. In FEM it is linear. uh, so in FEM, the training points are the point values what we are getting by discretizing the mesh. And here the parameters and the training points are nothing but the weights and biases and the collocation points generated within the domain. Now, it's not like it's the best thing came into the market. So there still exist, though pin are very much capable of handling high dimensional differential equation, complex boundary conditions, but uh, there is still exist some challenges on which researchers are currently working upon. So the first challenge is to improve pins accuracy and efficiency. Yeah, so it has been observed that pins were able to solve differential equation, even the complex differential equations, with sufficiently good accuracy. But again, it was not for all type of problems. So in some cases it gives a very good accuracy. In for some problems the accuracy is not up to the mark. So the first challenges comes is like how to improve pins accuracy and efficiency. And then what was happening in the pins is in the original pins. Let us suppose we have the domain of spatial domains and the temporal domains. So we generate in standard pins, we generate the collocation points randomly within the domains. Now, what happened? There are certain problems where the PD residual is higher at some points in the domain and lower at some other points of the domain. So overall, when the loss function is minimized, it is not. So the accuracy is so it has been observed that the accuracy is affected by the way we are generating the collocation points. So the one way of improving the pins came is like how to generate the collocation points. Now, the third thing is observed is how to improve the loss function. Because if you now have a little bit of idea how the loss function is generated, the loss function is the sum of the PD residual plus initial condition plus boundary condition. Now when we generate this type of loss function means the weightage of all the residuals are same, but that's not the case when we deal with the different type of problem. In some problems, the weightage of the PD residual is higher, or in some problems the weightage of the boundary conditions are higher. So one way to improve the spins algorithm is how we can improve the loss function, so that the, of course, our target is to improve the accuracy and efficiency. And the fourth way is how to modify the neural network architecture, how to improve the constraints in the pins that is being considered. So now, based on these challenges in the neural network, so some improvement in this area has also been proposed, and which I try to bring it over here is, first of all, is the residual based adaptive refinement, which is called as the RAR. Now, this is the improvement of one of the challenge what I mentioned just in last slide is, in pins, the collocation points are randomly generated. So what happens, because in some cases, the residual at some points is more than the residual at other collocation points. So what we do in residual based adaptive refinement is, first of all, we train the network with some set of collocation points and then calculate the residual at the set of collocation points, and then we see the points where the PD residuals are higher. We within the training process, we generate more training points at the points where the PD residual is higher. So that's what is the idea, that add more residual points in the locations where the PD residual is large. And we do this the process until the mean residual error is smaller than some threshold value we are choosing. So this adaptive refinement is proposed by Lulu in I think 2021 around, and is published in this paper. So we can see in this example where the Burgers equation is solved using the pins and the pins with the residual based adaptive refinement. So it can be visually see that this Burgers equation has steep solutions at the point at x is equals to 0. So what has been done is, instead of using the collocation points, like randomly generate the collocation points within the domain, more training points, or the residual based adaptive refinement is done at the point x is equals to 0. And from the results we can see that we can achieve the similar level of accuracy in the pins when we are using, okay, sorry. So we can achieve actually the similar level of accuracy with 2,540 points, and when we are using the residual based adaptive refinement. So of course, when the collocation points are less, our computational CPU time and complexity also reduces. But if we are using the standard pins, it requires 10,000 collocation points to achieve the same level of accuracy. So this is the one of the improvement in the standard pins, that instead of generating the collocation points randomly throughout the domain, we can observe the problem and see if there are steep boundaries. We can generate more collocation points there. And then nowadays, as I said, that this is actually a very demanding field these days, and people are working a lot. A lot of researchers are working in improving the standard pins. So we can find several variants of pins: G pins, X pins, variation pins, and many other. So One of the variant I try to bring over here, because I mentioned few of the challenges. One is the residual base, so which of course we can do with the RAR, and another I mentioned is improving loss function. So how we can improve the loss function so that it has some weighted residuals corresponding to each factors, or some other thing. So gpins is one of that. So in gpins, what's been done is a new type of loss function is constructed by using the information of just not only the pd residual. They use the information of the gradient of the pd residual also. Right. So in pins, basically what we were doing is this. If you remember, we were doing nxt minus fxt. That we were saying it is approximately equals to zero. So in G pins, we know that fx is zero for any x, but we know that if this is equals to zero, the derivatives of f will also equals to zero. So what's been done in this gpins is the derivative of this fx is also computed, and that will be equals to zero. So now when the loss function is constructed, it is not only the sum of the PD residuals, initial or boundary condition. It has one more term, if you can see that, which is summation of I is equals to 1 to D LGI. And LGI is the loss corresponding to the PD residual. Right. So if you can see, if I can relate it with the standard pins, I already mentioned, let us suppose LF is the loss corresponding to the PDs, LB, LI is the loss corresponding to the boundary condition and initial condition, and LGI is the loss which we are representing with respect to the this gradient. And how there is also a role of this wf, wb, and wbi, which I mentioned is, again, everyone is not equals to one. I could have write it lf, lb, and li. So that means all the weights have equal weightage, but not if we give different weights to different type of residuals, it can be optimized and find out which residual has the uh, higher effect. And this LGI is nothing but represented with this way, where LGI is the residual points for the derivatives, and remaining all this LF, LB, LI is the same meaning as we represented in the standard pins. Now, based on this idea of the G pins, so G pins has been applied on like several other problems, and is already been applied to many engineering application problems. So let us suppose we want to solve this 1D Poisson equation using this G pins. So it's been solved using GPINs, and from this figure, we can. So what has been observed that this GPINs is very much depending upon how we are choosing the number of training points, and how the weights of this loss function is being chosen. So from this first figures A, B, and C, we can see that if the training points, you can see that if the training point is 10, this blue is representing the L2 error with respect to pin. And sorry, this is representing with respect to pin, and this is representing with the upper line is representing with respect to G pin, and this red line is representing with respect to G pin when the weights is 0.01. So now you see that when the number of training points is increased from 10 to 20, first of all, the one observation is when the weights are chosen one. So weights are chosen one means WFLF plus WILI means the weights the weights we are having for initial condition PD residuals. If it is one, means we are using it as a standard pin. It is even performing worse than the original pins. You can see that over here. But if the weights are chosen different than one, let us suppose zero point zero 0.01 in is being chosen. So the G pins in the red lines, we can see that it outperforms the pin as well as the G pin with weight equal to 1. And when the training points is also increased from 10 to 20, we can very easily see that the L2 error is reduced while increasing the training points. So this second figure B is also representing, this is the L2 relative error with respect to the derivative. So again over here we can see that if we increase the training points from 10 to 20, the G pins with weighted loss function outperforms G pins as well as the pins. And further one more thing is also can be improved while we are dealing with the challenges of the pins, is how the loss function is constructed. So 2 minutes. So the loss function is can be constructed in a two ways. One is the hard constant and one is the soft constant. So the way I have presented in this talk is the way of constructing loss function using the soft constraints. Soft constraints means the loss function that we have constructed is not satisfying, is may or may not satisfy initial or boundary condition. But hard constant means we are constructing a loss function in a way that it satisfies boundary and initial condition. So it has been also observed that when the G pins are used using the hard constant means we generate in a way it satisfies the initial boundary condition. So when G pins are used with the hard condition, it outperforms pins with the hard condition, G pins with the means hard is performing better than the soft condition when we are using, and it can be seen from the figure H, I, and J. So meant to present first of all the pins, and then what is the current research nowadays is how to improve the pins algorithm. So two of the ways I have presented, where one way is one needs to improve the pins in terms of how the training points are generated. Other way is we can improve the pins how the loss function is constructed. Similarly, there are other variants also, which of course I could not cover it over here. Is one is the X pins, another is the variational physics informed neural network. So these all have different ideas. In X pins, it is based on the domain decomposition. Let us suppose we have a bigger domain, and then domain we discretize the domain into subdomains, and each domain we fit a pins and then find out the overall residual error. And this HP pins, V pins is also some variation in the physics informed neural network. So that's all about my talk, where I wanted to show that how the mathematical perspective of pins is working. Now, there is still a lot of work can be done in this area. One is, of course, because any of the deep learning or the machine learning algorithms are basically depending upon the random set of parameters, where the weights and biases are basically generalized initially, randomly generalized, initialized, sorry. So it is difficult to do its convergence and the stability analysis because it is totally problem dependent, and it is basically depending upon the set of random collocation points. So one direction where one can think about is how we can do the stability and the convergence analysis of such type of algorithms. Further, the new algorithms can also be proposed by using the efficient neural network architecture. So I know one of my student is currently working upon how to optimize or how to find out the best neural network architecture while training the pins, which is called the NAS pins. And further, one can think about to apply pins for solving some more complex, strong coupled multiple PDs, which whether to see whether pins or G pins or any of this variant are able to deal with such type of complex problems. And one can think about how to improve the training strategies in the neural networks apart from LBFGS, Atom, and other kind of optimizers which we are choosing. And other thing is one can come up with other way of generating the collocation points than we are doing the residual adaptive refinement. So yeah, these are the directions where one can think about how to deal or how to improve pins, and how pins can be used for solving PTs. So yeah, that's all about my talk. And if anybody having any question, feel free to ask.
In which the students learn how the pins physics information based neural networks and how they can be created, how they can be useful in their research. If any one of you have some question, then here can see ask.
हाँ हाँ थैंक यू मैम मैं एक एज ए ले मैन आई वांट टू आस्क वन थिंग कि देयर इज ए मशीन लर्निंग एंड वी आर थिंकिंग साइंटिफिक मशीन लर्निंग while machine learning is based on data science. So that is also a sign. So are you not thinking ki words are confusing? If
Uh,
scientific,
yeah, actually it's not like that. So the word, the coin, the scientific machine learn my sorry scientific machine learning word is coined
Hmm,
when basically we are not dealing with the data, because sometimes data, what were happening in the in the usual machine learning models
hmm,
is data is generally being fed to any of the machine learning algorithms, and it is kind of a black box model.
right.
So now we are saying, instead of just putting data into any of the machine learning algorithm,
Hmm,
so what we are doing in this field, data
hmm,
plus we are having some knowledge, some domain knowledge of how those datas are generated, from where those datas are come. So like for example, and let us suppose we can take an example of the COVID. So, okay, in the COVID, we have the data. For the COVID, we have the data about the factors, as well as the number of patients, number of people gets infected, hospitalized. So, one way of the research people were doing, like, okay, we have the data from WHO, we have the data from India or others, and just fed the data, use any machine learning models, and then predict it. So
hmm.
that's the one way machine learning is doing. In
That is
scientific,
that is conventional machine learning.
yeah, conventional, yeah.
Conventional machine learning.
But
Yeah.
what in scientific machine learning,
Yes, ma'am. Hmm,
what's the new in this data. Let
hmm,
us suppose the terms of equations, and it's already been done also. We are fitting five. We are just giving the data
hmm,
plus the equations that are representing the parameters of this COVID. So what happens? We are not only having the data; we are having the some domain knowledge also. How this data is depending upon so many factors.
hmm.
So that improves the prediction capability, and then it is called, the term is coined as the scientific machine learning.
Ma'am, in this, actually, whatever the physics we have involved, it is appearing in form of operator,
Yes,
eh?
equations.
Equations. And
Yeah.
equation actually becomes the operator on the function,
Yes.
and then it is executed. So one can easily, we can communicate to our students, it is nothing but the operator machine learning in which physical science is formulated in form of. operators, which is obviously the partial differential equation.
Yes, yeah. So that's the name is being coined and is being used. And if one come up with any other little bit of idea and can coin other name is also
Thank,
also.
thank you so much, ma'am. Thank you.
Thank you so much, sir.
Any other question? Now I invite Miss DP for formal vote of thanks.
Thank you so much, sir. Good evening, everyone. On behalf of Department of Mathematics, CCS University, and organizing committee of this 5-day workshop, I am DP, research scholar. Feel honored and privileged to deliver the vote of thanks. First and foremost, I express our heartfelt gratitude to our extreme resource person and speaker who made this workshop truly enhancing. We are extremely thankful to Dr. Neha Yadav, Assistant Professor in NIT Jalandhar, for her insightful and deeply informative session on physics informed neural network, a mathematical perspective on solving differential equations. Her expertise in numerical analysis, scientific computing, deep learning, and PD greatly benefited all participants. We sincerely appreciate the time and efforts you devoted to guiding us. Thank you so much, ma'am.
Thank you so much. And I thanks again to the organizers for giving me the opportunity to talk and present my work.
Thank you, Dr. Neha. Thank you.
Thank you. I must sign off now. Thank you.
Okay. So tomorrow we will assemble at 9 a.m. The breakfast will be in the department. So all are requested to be in time at 9 a.m. After 9 a.m., the lecture will start at 9:30, and that will be in physical mode. And Professor S.P. Yadav from IIT Roorkee. And after that, Professor S.K. Pandey. He will be in the physical mode, offline mode. So before lunch, the sessions will be in offline mode. So all be in time. Thank you. Thank you.